All right, from last lecture, we had where we found the area bounded by two graphs, y equals square root of x and y is equal to x squared, where we had to find the upper bound, the lower bound, and we had to take this area right here and find a typical rectangle here. Remember, we would have this typical rectangle where this would be our dx. That's our width. And then our length would be our upper bound minus our lower bound, okay? Which in this case, it was square root of x minus x squared. All right, so that leads us into, whenever you integrate with respect to x, you must have a typical vertical rectangle. Your width is your dx, always with respect to x. For a vertical box, it is top y minus bottom y, okay? So that's that one. So what if I asked you to, let's say, find the area bounded by y equals x squared and y equals x cubed with respect to y. All right, so with respect to y. Okay, well, this is if we had done this with respect to x. So how would with respect to y change? Well, let's look at that. Okay, so whenever you integrate with respect to y, you must have a typical horizontal rectangle. Your width is your dy, and that's always with respect to y. For a vertical box, it is right minus left. Okay, so if I were to draw this out, okay, all right, we have y equals x squared. Okay, so we'll say that that one is x squared. And let me change this to green for x cubed. So let's say x cubed would kind of look like this. Okay, this is not exact, but I just wanted you to see this kind of difference, okay? And I'm going to make this pencil really small so you can kind of see this, and I will do this in red. So now we have a rectangle that's a horizontal rectangle where this is our dy, and then we're going to have our right function minus our left function, okay? So in this case, let's do that. This is my x cubed. Okay, so I have the right minus left. Well, that is, well, the right function was my x cubed. My left function was my x squared. And then the width is dy. Okay, so we can set up this integral. Okay, so the area bounded by this function is going to be our left, or our right minus our left. However, notice that if I were to put this in here, x, please don't write this down. And I did that, well, I'm dealing with x's with a dy. Okay, that's a problem, all right? Because these x's, if I were to integrate with respect to y, I can just factor out the x cubes. So what I really have to do is I have to convert these into functions where it's x equals, okay? So if I have, for instance, y equals x cubed, to solve for x, I have to get rid of the cubed. The way to get rid of this cubed is to take the cube root of both sides. Okay, so really x is equal to the cube root of y. All right, so this becomes the cube root of y minus whatever our x squared is. So let's do that. Well, if I take the square root of both sides, okay, this is a square root. This gives me x equals the square root of y. And we don't have to write the 2 is implied. So instead of saying x cubed minus x squared, it's really the cube root of y minus the square root of y, okay? So here we would put those in. So let's do that. I'll just rewrite this. So this is going to be the cube root of y minus the square root of y dy, okay? But now we have to find our limits of integration. Now remember, when we're solving these, we have to integrate with respect to y here. So typically we would have just done this, x squared is equal to x cubed, and solved for x. Well, we can still do that. So let's see, x cubed minus x squared, factor out an x squared. This is x minus 1 equals 0. So 0 is equal to x squared, and 0 is equal to x minus 1. So x is equal to 1 and x is equal to 0. Except if I use the x's here and I integrate with y, that's not going to work. So what I have to do is I have to figure out if 0 is x, what is my y? Well, remember, y is equal to, and I can use either this function or this function. It really doesn't matter. I'm just going to use the x squared. So if x is equal to 0, 0 squared is still 0, okay? And so this is my x, this is my y. And then let's do this for 1. If x is equal to 1, 1 squared is still 1. So this is my xy. So I'm going to go from 0 in my y up to my 1. So 0 and 1. Now it just so happened that this is x, y happened to both be 0, 0, 1, 1. But this could have easily been, say, 0, 0, and say 2, and 2 squared would have been 4. Okay, say we were looking at a different piece, then it would be 0 up to 4, because we're dealing with y equals 0 and y equals 1, not the x's. Okay. All right, now let's go ahead and solve this. So we have the cube root of y. Well, from 0 up to 1, we could say that this is y to the 1/3 minus y to the 1/2 dy, which gives us y to the 1/3 plus 1. So 1/3 plus 3 over 3 is 4/3 over 4/3 minus, that's a 3, by the way, okay? Y to the 1/2 plus 1 is y to the 1/2 plus 2 over 2 is 3/2 over 3/2. And we're going to evaluate this from 0 up to 1. So we're going to get 3 times 1 to the 4/3, which is still 1, over 4. And then 1 into this, 1 to the 3/2 is still 1. So this is times 2 over 3. And then minus 0, when I plug in 0 there, it's 0, and then minus 0. Okay? So this is 3/4 minus 2/3. Finding a common denominator is 12. So to get 12 for 4, I have to multiply by 3. 3 times 3 is 9. And then 3 times what gives me 12? What's 4? 4 times 2 is 8. So this answer is 1/12. Okay? And I want you to notice that the last time we did this problem, y is equal to x squared, y is equal to x cubed, and we were finding that area, it was 1/12 when I was doing this with respect to x, okay? So notice here, I end up with I'm sorry, that's y equals x squared. Did I do x cubed? Yes, here we go. Okay, so I had 1/12 for f of x equals x squared and g of x equals x cubed. Okay. Again, if you notice with that last problem, I did not specify with respect to x. So if I don't specify whether it's with respect to x or with respect to y, you can do either. You can do your typical horizontal rectangle and do it with respect to y, or you could do it with respect to x and have the typical vertical rectangle. Okay, so unless it specifically spells out with respect to x or y, you're still going to get the same answer, but your area formula will look a little bit different depending on if you go with respect to x or with respect to y. Okay. All right. So let's talk about solids of revolution. Okay. Let's talk about solids of revolution. Let me go back to my regular marker. So solids of revolution. Okay. So what we've been talking about so far is these functions, say x squared and x cubed, and then we had some area here. Well, what happens if we go from some a up to some b, and we have some function here that we're going to revolve around our axes, okay? So we're going to take this and we're going to revolve it around our axis, okay? So we're going to take that function, we're going to revolve it around the axis, okay? Say around the x-axis. In this case, if it's solid, we're going to have that typical rectangle. Let's assume it's this one, okay, that we're going to go all the way around, and that's going to be our width, and that's going to be our delta sub x, okay? So let's do our, okay, so here's our definition. We're going to let f be continuous on some a to b, okay, some closed interval from a to b, and let r be the region bounded by the graph of f. The x-axis and the vertical lines x equals a and x equals b. So here we go. Here's my x-axis. That's our x-axis. This is the graph of x. I'm sorry, f of x, okay, or our graph of f. And we're going from some a up to some b. Regardless of what the function is doing out here, we're just looking at this area right here, okay? And we're bounding this by from A to B, and we're bounding it by that portion of the graph. So it's going to be revolving around the axis, okay? If it's about the x-axis, we're going to use this formula. The volume is equal to pi times the integral from A up to B of our function squared with respect to x. So this is going to be dx. If we were to have revolved this same function, okay, so we have this function from A to B, okay, and we were going to revolve it around my y-axis, okay, so essentially it's going to revolve this way, okay. We would go, the volume is equal to pi from A up to B of our g of y function, quantity squared dy, because then we would have our vertical rectangle, our rectangle here. Okay, that would be our dy as it's revolving around my axis. Okay, and in general, it's pi times the radius squared times the thickness. Okay, so that's kind of the in general. Okay, so let's do an example of this problem. So let's go over here. So let's calculate the volume of the solid of revolution generated. So again, this is a solid by rotating about the x-axis, rotating about the x-axis. The region of the xy plane that is bounded by y equals x squared, y equals 0, x equals 1, x equals 3. Okay, so let's kind of draw this out to kind of see what they're asking for. So here's my y equals x squared. Okay, that's my y equals x squared. So that's x squared. This is my y-axis. Okay, my x equals 1 and my x equals 3. So I'm going to go from here to here. Okay. And I am going to revolve this, let's say around here. So if you were to kind of think about, I'm going to do this in a different color so you can kind of see what this would look like. So this is going to continue on down here to kind of look like that. Okay, so we're going to have this volume of this solid from 1 up to 3. So we're going to have the volume is equal to pi times our integral from 1 up to 3, and that's our hint right here, our x equals 1 and x equals 3, of our function x squared, quantity squared, dx. Okay, so we have one function, we're going to square it, and then we're going to evaluate from our limits. Okay, so from 1 up to 3. So we're going to have pi times, well, x squared is x to the 4th. So when I undo that, it becomes x to the 5th over 5 from 1 up to 3. Okay, so this gives me pi times 3 to the 5th over 5 minus 1 to the 5th over 5. So this gives me, what is this? 243 over 5 minus 1, so 242 over 5 pi is the volume that is generated when you revolve this around my x-axis. Okay. And I could have said this is, oh, this already said rotating about the x-axis. And they gave us our x equals 1, x equals 3. They have, these limits have to be given. Otherwise, I mean, this could go to infinity, really. I mean, we don't know. And it could start at 0. All right. All right, let's do another example of this. Okay. Let's calculate the volume enclosed when the graph of y equals x cubed when x is between 2 and 4, I just wanted you to see this can be written lots of different ways, is rotated about the y-axis. One thing I want you to recognize with each of these is this is telling me volume. If I go back a couple pages, these were finding the area. So that's why there's a big difference. These, you're just solving for that little area between, say, two functions or under a curve or something, and you would have an area. A volume is when you have, you could think of it in 3 dimensions, okay? Volume would be, say, length times width times depth or height, okay? Now this one is telling us the y-axis. All right, so they tell us that y is equal to x cubed. So I have to turn this into x equals something. Well, what is that? To get rid of the cube, I have to take the cube root. So x is equal to the cube root of y, okay? So my, let's look at what this function looks like, okay? And what they're asking us to do. X cubed looks like that. And we're going to go from 2 up to 4. We'll say 4 is right here, okay? From 2 up to 4. But we're not going along my x-axis. We are actually going to rotate around my y-axis. So really what we have, let me do this in a different color. Let me do this in purple, okay? Really what we have is we have almost this bowl shape, okay? And we're going from this point to this point. So over here, and over here, okay? So really this is the solid that's being generated, is like this, okay? So again, we would have our typical vertical rectangle, horizontal rectangle. This is our dy, okay? So what we have is we have the volume is equal to pi times our integral, and we have to figure out what those limits are of our function. And our function was the cube root of y, quantity squared, dy. All right, so now we have to figure out what our limits of integration are. Well, they tell us it goes from 2 up to 4. So let's do our little xy. And we want to figure out what y is when x is 2 and what y is when x is 4. So let's use this function. When x is 2, 2 cubed is 8. And when x is 4, 4 cubed, that's 4 times 4 times 4, so that's 64. So this is going to be from 8 up to 64. Okay, if you use 2 up to 4, you would be doing across here instead of along here. All right, so let's see, pi from 8 up to 64, and this is y to the 1/3 quantity squared, so this gives me y to the 2/3 dy, because remember this is y to the 1/3, and that's squared. That gives me y to the 2/3. Okay, so let's see, pi times y to the 2/3 plus 1, so that's 3/3, so this is y to the 5/3 over 5/3 from 8 up to 64. Okay, so this is pi times 3 times 64 to the 5/3 over 5 minus 3 times 8 to the 5/3 over 5. Okay, well, we can calculate this out. So 64 to the 5/3, here's a quick little hint. You can factor out the 3/5, so we have 3/5 times pi times 64 to the 5/3 minus 8 to the 5/3. Now remember, we'll be able to do both of those because we can take the cube root of 64 and we can take the cube root of 8 and then raise that to the 5th power. So really what we have is 3 pi over 5 times, well, the cube root of 64 was 4 to the 5th, and then 2 is the cube root of 8, 2 to the 5th. When we subtract those, we end up with 992, which gives us 2976 pi over 5 is the volume. Okay. All right. We'll go ahead and stop this here. Our next lecture, we're going to talk about washers and shells.